Live from downtown Mill Bay.
Yo, dude, chill. Oh, please don't shoot me.
Zane? Who was planning to shoot you? Science 10. Schedule. Science 10 attendance. Ooh, looks like we should be all here. Timmy? Timmy. There we go. Ben.
Here.
And Jonathan.
Yep.
Ariel. Zoe. Lisa. Felix. Zane.
Yep.
Matthew. William K. Alejandra. Bertie. Zachary. Kieran. William R. Naomi. Hugo. And Sahir. Excellent. Okay. So last day we were doing, looking at the number of valence electrons and then looking at most likely electronic charge. Having this done, as you may notice from your periodic table, things tend to go up in a fairly periodic fashion. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I will stop counting out loud because I feel like I'm in kindergarten. Now we tend to stop at calcium because then you get into larger electronic structures, can get a little complicated. You still could do them though. We still have the, how many electrons fit in the first shell? Two. Second?
8.
Third?
8.
Fourth?
18.
Excellent. That's also a bit of a lie, and a little with the Bohr model I can show you why that's a lie if you're interested. Now for the electronic structure you should notice a clear pattern. We have 1, 2, and then once you go there, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 2, 7, 2, 8, and then 2, 8, 1, 2, 8, 2, 2, 8, 3.
What?
Yeah.
I don't think
Can't see it if you're writing on the.
Oh my God.
which one are you talking about? I wasn't realizing.
I've just been saying words, and you've all been staring at me and looking at Google. That's what I've been doing. Although, it would have been live streamed correctly at least. Although nobody's not here, so that almost doesn't make a difference. And now we can make some observations. What is the number of valence electrons in every single one of these elements? 1. There's one outermost electron, one outermost, one outermost, one. So in every case, it has 1 valence electrons to play with. That's what gives them all very similar chemistry. When we do the periodic table, we're going to call these an entire block like this. Does anybody know what a column of elements is called? That one has a specific name, but what's it called in general?
A column of elements. A row?
Other than that, yeah?
Is it a group?
It can be called a group. Yeah. It's a family. Because they all share similar characteristics. And even if you're adopted, they pick up on their family's habits and do exactly the same things. I got into a lot of trouble a couple of weeks ago because I mentioned to someone, they started talking, and then they did all the gestures exactly like their mother. I'm like, you just transformed into your mom for a second. Apparently, that can be a very great insult. Word of warning in case you're talking to people. So this is known as a family. Can be called a group. And if you want to be pedantic, it could be called just a column. But we refer to it as family because they share characteristics. Now, they share characteristics, and then there's something completely different. And then you share the characteristics again, and then different. And then you share the characteristics again, different. So the same characteristics crop up periodically. That's why it's known as the periodic table. That's how it was first constructed. A gentleman in Russia, Mendeleev, went through, had a bunch of elements, and he just stacked the ones that had similar characteristics on top of each other. He put the lighter ones on top, heavier ones on the bottom, and he started creating families. He noticed certain trends, and he started putting the order, and he constructed the first periodic table. What do all of this family here have for valence electrons? 2. So you should get 2 for every single one of these, because they all have 2. And as you go across, we get... It's not a trick question. Say here. How many valence electrons in the boron column? Boron family. No. How many valence electrons are the Just boron and aluminum. What is a valence electron? It is the outermost electron. Ahem. When someone says something, if it's clearly wrong, please do not chuckle or laugh. This should be a safe space to get things wrong. I am now going to share something with you because you should know who you're getting taught chemistry with. I took chemistry 12 and I got 51%. And I'm teaching you. The reason I got 51% is because I only really cared about physics. I was in honors physics. I got an A in honors physics. And then I went to university. And I found out all of the honors physics people smelled a lot. I mean, I was nerdy. They were so nerdy they didn't believe in hygiene. So I was like, these are not my people. I switched into computer science. And it turns out computer science is the exact same set of people. Like, there was no difference between the people. And now that I say that, I won't bring it up. I found a post yesterday that said, can I go to my teacher and tell them that the class stinks and encourage everybody to have a bath? The comment right underneath it was this a computer science class? And they were like, yeah. So then I switched into chemistry. And I did an entire bachelor's in chemistry. I also did biochemistry, so I have a biochemistry major. But at the time, I didn't do well. I would have asked very dumb questions in class. People can't learn without asking questions. So if someone says something, you can help them. So you can turn around, you can tell them the right answer, you can tell them what it is. But please let people give the answer that they need to give so that they can be wrong. Also, please don't interrupt me when I'm talking. Put up your hand when you need to, and sometimes I'll just ignore it because it's not quite yet. Okay, there we go. So back to here, the valence electrons is the outermost electron. How many outermost electrons does boron have? 3. And how many does aluminum have?
3.
So it has 3 overall for both. And so we're going to see that as a pattern. So I'm going to ask you here again, how much does the carbon group have? 4. Excellent. And then everybody can predict, as we go across, what does it become? Everybody. 5, 6, 7, 8, no. 2. So we got 2 up here. There's 8 and 8. So it doesn't quite fit the pattern, but we can't. What can we say about the valence electrons there? Yes.
It goes 2, 8, 8, like
how electrons work. So these are all full. That is definitely true, even if it's not maximum. Because if we go down any further, we would actually end up with 18 here, and so it would kind of violate that a little bit. That is a little sick. Now, the next one, I ask you to write the most likely charge. I am not going to redo that on this one. If you could just move down, I am just going to alter this one because that would be a little easier. If I was to make the most likely charge, How many people added an electron and got 2 here? Nobody. How many took that electron away? Some people. So if you took that electron away, instead of having valence electron, what would that charge be?
+1.
And that's what we do with all of them. You have 1 electron. Do you add 7 to make the outermost layer full? Or do you take 1 away to make it empty? Take away. Electrons are lazy. They want to do what's ever easiest. Having 1 go away is easier than inviting 7. And so in every case, you will find that it doesn't have anything in its outer shell. And they all end up being what charge? Positive 1. Here you go.
You could add 7 electrons to lithium,
You could,
but I mean, it's 3 protons against.
yeah, the fight it would have to keep hold of them. This nucleus is not very attractive to hold on to a total of 10 electrons. 3 protons, 10 electrons, not really going to happen. I say lazy because that's a metaphor, but it is down to the charge. This is positive, that's negative, it's too much negative charge. So it can give up 1. Yeah. Luke? Don't call it class. Too much. Questions? Questions in the back? Question? Nope. Okay. So as we go through, then, what would we do here? Eliminate 2 or add 6? 2. So we go through. What would the charge be if we eliminated 2? Plus 2. And they all do that. What would we do here? What would the charge be? Plus 3. I'm going to get rid of that. So this would be plus 3, plus 3. Now we get to here. Are we going to add 4 or take away 4? And I'm going to ask someone in particular. So actually, don't call it. I will ask Kieran. Do you add 4 or take away 4? Take away 4. He believes in taking things away. Karen, what charge would it be if you took away 4? Plus 4. Did anybody here add 4? You can. Because at this point, it's 6 of one, half a dozen of the other. It's 4. It's right in the middle. You could do that. So if you got 2, oops, I'll pick a different color. 2, comma 8 and 2, 8, 8, and you put minus 4, that's okay. You're allowed to do that. Because carbon and silicon have twice the chance of a date on a Saturday night. They can ask anybody out. If their partner wants to give them electrons, they'll take them. Their partner wants to take electrons, they'll take them. It doesn't matter. They're willing to do whatever it takes to please their partner. Whereas boron has to get rid of 3 electrons. It has to find something that will accept 3 electrons, or at the very least share them if we're going to talk about covalent, which you may have done a little bit last year. But once we get to nitrogen, let's go with Lisa. What does nitrogen do? Take away the 5, or what else could it do? Shh. Oh, you can't add 5. What's the maximum that can be here? Add 3. Which sounds easier, adding 3 or taking away 5? Adding 3. So really, this would become an 8, and that would become an 8. If I add 3 electrons, what charge is it? If you add 3 electrons, it would be minus 3. Each electron is negative, so you get the same negative charge as the number of electrons you add. Ben, what about oxygen? Yes. What would oxygen do? Or sulfur?
Like in what terms? Like the daily shell?
Ben, were you following along with the last 3 examples?
I was
got to pay attention as we're going through, because otherwise you get a surprise question. So in the previous one, it was 2, 5 there. So we added 3 electrons. We want to make the outer shell full or empty. So to make this one full, we'd either add 2 or take away 6. Which do you think it would do?
No, take away 6.
Take away 6. Which sounds easier? Taking away 6 things or adding 2 things?
Oh, I guess adding 2.
Adding 2. So once we cross this line, this is the middle. It could go either way. But once we cross that, everything becomes negative.
Wait, are you talking about ionic bonds?
No, we haven't even discussed those yet. But we're getting there.
But isn't that when you share? Isn't that when you share?
No, covalence when you share.
But are we on the upper? Sorry,
No, I'm doing this one on this.
Oh, okay,
There you
no,
go.
I understand now.
Okay. Now, if you added...
I just thought you were still doing the first one.
No. If we are adding 2 electrons to this, what charge would it be?
Negative.
Negative 2. Excellent. Do the same for this one. If you have 7 outer electrons, would it add 1 or take away 7?
Add 1.
Add 1. So we get 8. And then what charge would it be?
Oh, add.
You added 1 electron.
Oh, so negative 1.
So negative 1. Excellent. Well done. Now, what would... William, K. What would this column do?
It wouldn't do anything.
Wouldn't do anything. Why?
Because it already has a full valence shell.
Has a full valence shell. It's happy. That's why they're called the noble gases. People who sit in castles with tons of money don't do any work because they don't have to. They have everything they could want. That's why this whole section family is known as the noble gases. They're not going to engage in any bonding. They're not going to give up any electrons. They're not going to add any electron. They have everything they need. Whereas everybody here doesn't have everything they need. They either have to add or take away. Yes?
So if it has a full valence shell, like it never will have a charge.
If it sorry, say that again.
Like if it has a full valence shell, will it never have a charge?
The noble gases have a full shell without a charge, but every single one of these has a charge to get to that configuration. Right. You can also look at it as that all of them are trying to become like a noble gas. These ones were all trying to become like neon, but which one did these ones become? Helium. So these ones became like helium. They gave up their electrons to have a full shell like there. These ones added electrons to become like neon. And you'll see a similar pattern here. Which one are these ones trying to become like? Argon. And then these ones are trying to become the previous ones, like neon. Now, I did not draw on this one because I didn't want to redraw all those things, but that should be reflected on both of yours. Now that we can determine what a valence electron is, we are going to do Lewis dot diagrams. Curiosity. How many of you did Lewis dot diagrams in grade 9? Ooh, a couple. Excellent. So you've seen now who the experts are. They should be able to do everything with no problem and teach everybody around them. Identified. We're going to do 2 types. One for individual atoms. And the second one, if you put them into a compound. Now, where's... Someone has stolen my stick. There's one of my sticks. Looking at the same sheet we just did, how many valence electrons did hydrogen have? How many did helium have? 2. Yeah? How many did lithium have? 1. How many did beryllium have? How many did boron have? Not 5. 3. I want you to notice something. This is the way to get the valence electrons really quick. In this row, how many over is boron? How many valence electrons does it have? 1, 2, 3 over.
Oh.
Okay, so you got to count all the way from here. How many valence electrons, counting, does oxygen have?
6.
Hands up for 5. 6. 7. Because I heard someone say 7. So 1, 2, 3, 4, 5, 6. So just to make sure that there's nobody hiding, I'm going to point to an element on here, and you're going to tell me how many valence electrons. We're going to start at the back, right? So how many valence electrons does helium have? Next up, I'm just going to just go across, and then we'll just go up this way. So next,
6.
and then so here, we're going to go back there.
1.
Mm,
3.
yep,
5, 3.
5.
They're cool.
excellent. Moving up 1.
1 color is 1.
7.
Excellent. And let's just move up again because the row's here. So,
You don't color. 2. 1.
excellent. And right there we'll go
4.
and
3.
excellent. Matthew,
5. Sorry, 8.
excellent. And now, skill testing question, because now we're getting down to the end. I'm going to go, yeah, right.
3.
Excellent. So,
7.
excellent. And let's go with, no, that one.
Yeah.
Yeah, because it was right underneath it. Now, skill testing question, and I will warn you, there is a trick.
13. Don't pull. To me.
Yep,
5.
very close.
Not close.
It's so close.
6.
No, the other way.
14.
Louder.
4.
4. There's 4.
But why? Oh, wait, I'm dumb.
No, you didn't know the trick. So, when we counted in here, we just added, so there, how much does this one have, everybody?
4.
4. That one?
8.
8, sure. Now, moving along, I'm going to ask you that one.
A lot.
Yeah. 7. I'm going to ask you, let's go with that one.
I know what the
Shh. Nope. How did he get 7 for over here? No, he got 4 there. So here's the trick.
3.
1, 2, skip a few, 3, 4. You do not count anything in here if you're in this area. If you're in here, count them, sure. But if you're in this area, they go away. Okay. If you want to know why, I can explain it, but they just do. So if I said this, how many would that have? 7. So this actually has an interesting effect. How many valence electrons does this one have? What is that one? Doesn't matter now. Everything in here is the same number of valence electrons. And that's why they all share very similar properties. Because these electrons don't count. Yes?
But what about the ones that are hidden, like the ones that are
In here?
Yeah.
They don't exist.
No. They don't.
No, they don't.
No.
No, if you went to here and you kept counting, that would be fine. But if you are in here, like you counted to there, that would just be 1, 2, 3, 4, 5. Because if you filled this up, it also skips a few.
Okay.
So it would also happen there too, for similar reasons. Yes?
I got a question.
Yeah?
Slightly off topic, but like, let's say you take carbon there, right? It's either plus 4.
Take what?
Carbon.
Yeah.
Okay. It's either plus 4 or minus 4.
Yeah?
But let's say you took one of the gases that is either that
protons to an electron what they want,
Yeah.
right? So if, let's say, carbon is trying to get 4, but that one only has a pull of, say you pick, one of the little gases, let's say, NE, what's that one? Doesn't really matter, but say that it's trying to keep it, why can't carbon take electrons because it wants them more?
Oh, I see. Why can't they take from a noble gas?
Yeah.
When your electron levels are full, they settle into a lower energy level.
Oh, okay.
Okay, and you can think of it like clicking into place.
Yeah.
Would be, and they're much more difficult to rip off. Also, carbon and neon. Let's say you're trying to do it with neon. Neon has a lot more protons than carbon. In a fight, neon's going to win. Carbon can't take its protons, and it doesn't want any more. It can't give them to it either. Noble gases. So noble gases here at the end have the most number of protons than anything in its own element.
Well, what if you did, let's say, Si, and
So it has more protons.
yeah.
Right. Neon, again, they're clicked in. They're really stable. It's going to have a really hard time taking them from neon. Now, if you get it enough, neon may not bond, but if you did manage to rip one off, it's going to immediately get it from someone else who's weaker.
Okay.
Yeah. They won't bond with it or anything. Yeah. A really unstable atom is like helium with no electrons, which you could do because they're only held on by 2 protons. Known as an alpha particle, it's a form of radiation. If it hits you, it causes cancer because it will take those electrons from anything. Yeah. Now you just know how to figure out the number of valence electrons for anything. If you really want to know why, I will do this very briefly. Because, of course, how many of you have heard a science teacher at one point say, we're actually kind of lying to you, or they lied to you last year, and here's how it really works? The reason we do that is not because we're lying to you, but we're giving more and more advanced models. And models are as good as the task you want to do. The Bohr model is great for all the chemistry we do. But if we go higher, and we need to do very complex models, because we want to make a drug and we want to know exactly which way the atom is going to look, we have to use quantum. So in the Bohr model, let's take bromine. Bromine would have 35 protons, and it would have a structure of 2. Please turn that off. 8. Whoops. 8. And then 17. And that's what I would expect you to come up with. The actual structure is this. Bromine has a structure of 2, a 2,6, a 2,6, and a 2,10, 5. So in addition, and so this is not that much more complicated. You've learned that there's these major things. This is 1, 2, 3, 4, right? Like they're in order. But there's sublevels. In the first one, there's only 1 sublevel. In the second one here, there's only 2 sublevels. There's a 2,6. And then the last piece of information is this 10 belongs to that sublevel. But it's a high enough energy, it doesn't get filled up till out here. Once this is full, so once you fill all of these up, that 10 literally bumps down and goes in here. And that's why bromine only has 7 valence electrons. Once it's full, it actually drops down to another level. That's the little qualification that quantum has made. There are sublevels, and those sublevels can move around after they're full sometimes. And in fact, we number them. So this is the first, this is the second sublevel, this is the third sublevel, and this is the fourth sublevel. And if I was to write out its quantum configuration, not Bohr, I would write 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. And now you can see that's where this comes in. Those two are these two. And we label different levels. The sublevels are called S, P, and D. Now, if you looked at that right now and were like, I don't ever want to hear about that again, you don't have to. We're not going to do it in grade 10. We do it a little bit in Chem 11. But this is just what's going on in the background. But we don't need to do that. We need to make Lewis dot diagrams. Nice segue, eh? So please get me, write down the number of valence electrons for Bohr and draw a nice Bohr model for sulfur. There was a hand up at the back, I think, and I ignored it for a second. No? Oh, I answered. Okay. Nice. I like it when I just naturally answer questions. And William R., what's the number of protons for sulfur? So here, why don't I see any notes in front of you? And see here, I may move you next class because this is the second time I've seen you with no notes. You've got to be focused. Maybe over there. I'll take it how you are the rest of this class for that. William, how many protons for sulfur? 16. And I'm going to ask someone, we don't really need it, but let's get an estimate of the number of neutrons. Felix?
Still sulfur?
Yep, still sulfur.
18.
18.
No.
Nope, you said 18. This is now an isotope of sulfur. Instead of being sulfur 32, you've clearly identified sulfur 34. It's now radioactive, and we're all going to die. It's fine. It's fine.
Yeah.
And then 18.
Wait, shouldn't it be N?
Oh, it should be N. My goodness.
I calculated wrong.
I will correct that in pink. Sorry. Yeah. There we go. We have pink, and then above it, we have dark pink. Yeah. Yeah.
Red is our pink.
Red is dark pink. Yeah. Yeah. Because Hope House rules everything. Yeah. Hugo, number of electrons.
Herschel is minus 2.
Two.
8
8
and 6.
and 6 electrons. So everybody should have something like this. And now I'm going to show you how this is transformed into the Lewis dot diagram. Hang on to your seats. We draw the symbol for the elements. The instructions are given above, but I'm going to show it to you. And then we add the electrons. We only add the valence. So here, how many valence electrons are in this?
6.
No, I said 6. Yep. 6, excellent. 6 valence electrons. So here's how we add them. 1 quadrant at a time. And you...
Wait, it's quadrant.
1 second. Quadrants are like north, south, east, west. The 4 quadrants, like a map. And the reason we do that is because they do kind of point in those directions. And we start doing one at a time. We go 1, 2, 3, 4. And we place them all separately until we run out. When we place all 4, we start pairing them. 5, 6. You remember doing this? Nice.
Oh,
Yeah, valence electrons.
we like mixed
So you
them.
only do valence electrons?
Pardon?
Just
Only valence. Because Lewis dot diagrams are used to show bonding and what the electrons are doing. And so we only care about the valence electrons. Okay.
okay.
What is on the next page? Yeah. So we got 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Oh, that's perfect. Yeah. Ignore all these. Because what I am going to do is I would like you. Where's the thing? I'm going to ask you to go to the board in a moment. Let's go for Science 10. Toolkit, Group Maker. Oh, I want groups of 1. Haha. I've put you in groups of 1. Why would I do that? Because it assigned you a number. That number is the atomic number of the atom I want you to make the Lewis dot diagram for on the board. Write your name above it, grab a thing, erase if you need to, previous stuff. Show me what you got.
So I just make it on my name?
Not there, on those boards. Don't write on the screen. And yeah, put your name on it, or initials. Be proud. Oh, that was, I totally should have excluded sulfur. Nicely done.
I have a question.
Yeah? I'm going to come around saying they're right, but it's looking good. Hold it. How many dots do you have around it? 1. Why? How many valence electrons does it have?
It has 9. I really don't get it. The way I think it was.
How many valence electrons does fluorine have?
No, yeah, that's the thing. I don't
So when you just look at the row it's in and count. 1, 2, 3, 4, 5, 6, 7. Once you're done, you can have a seat. Yeah, you put your initials and name on it.
I think it was our
Put your initials and name on it. You can use a code name.
Nothing. There's nothing.
Looking good. Looking good. I like high jumps here. That's good.
It's like this.
I'm not sure you have the right number for this electron. How many valence electrons do you have?
Sometimes what you have to do is you have to get the tip wet.
Look, you got your table mic on. No, in our size, how many is on the tip? 3, so you only need 3. That looks good. Once you're done, have a seat. Because there's lots of things in terms of style I just want to go over that's convention. It has nothing to do with actual chemistry, but how you write the dots. And I want to see if everybody naturally did it perfect. So we've got, this is good sulfur. That was totally cheating. They shouldn't have allowed number 16. The parallel, fluorine. Ooh, this does not have 1 valence electron. How many valence electrons does fluorine have?
7.
7. Because you count along from where you are. So you go 1, 2, 3, 4, 5, 6, 7. Quickly fix it. Helium. Oh, perfect. Will. And this is for everybody. If you were, this is only true for helium. You know I said go around and then only pair up? You only start pairing up once the half of it's full. So you go around for most of 1, 2, 3, 4. But for helium, when is it full? At 2. So you actually pair helium. Just because the 1s2 orbital is now full, so they actually are paired. Now, if you, as grade 10 students, do this, I'm not going to quibble about it because you're following the rules. But if you do this, you're definitely extending high because you know things. This looks good. That looks awesome. That looks fantastic. The other thing I'm noticing that people are just doing it automatically. I never told you to do this. You're creating these parallel to the atom, and that's how you're supposed to do it. Some people try to put it in line. You're not. They just convention. You're not supposed to do it. Also, if any of you were ever taught in a German school, you may sometimes see this. So draw the same thing as one, but instead of putting a pair, they'll go like this. So 2 electrons paired is sometimes represented as a line that is allowed, especially if you were taught in German. The boron looks good. We've got 3 around. Is there anything here I haven't covered? Nope, those are all fantastic. Phosphorus is looking good with 4. We've got oxygen and it's 2. Sodium only has 1. Now, Felix, now they're in the right spots, and this is that convention I talked about. Take the ones on the right and make them parallel with the F. Right now they're sticking out, and we just don't do it that way. I don't know why. Now, weirdly, both Felix and Bertie did fluorine, and fluorine is number 9.
Oh, I got it wrong.
Only Felix had number 9.
I got that wrong.
Bertie, you had 14. So you had silicon. And Kieran Porter, you had 12. Which means you had magnesium. Go do magnesium, quick. Hydrogen looks good, aluminum looks great, fluorine now looks good, sodium looks great. Okay, and phosphorus with, hold it, Jonathan? Phosphorus is missing one. How many valence electrons does phosphorus have? 5. Yeah. Pardon?
What are you doing? 2 at the top, 2 at the bottom.
Oh, what's the symbol for silicon?
Oh, yeah.
SI. Okay. Next part. This I just want you to notice. Once we have these, we start playing around, we're going to talk about ionic and covalent bonding reactions in the future. But one of the things to notice is that when we had, magnesium gets rid of its 2 electrons. You can see in there, it gets rid of 2. It'd be a lot to add more electrons. Sulfur can just add 2. But if they engage in covalent bonding, you can think of these little lone electrons as hands. Sulfur has these 2 paired. Once they're paired, they're happy, which is why we pair them with helium. They're happy, they don't want to be separated, they found their long lost love, they're running across into a field with open arms, they're great. So sulfur tends to have 2 bonds. Phosphorus tends to have 3. Who had carbon? There should be a carbon. Who was 6? Where did you draw carbon? Oh, awesome, up here. Pale green, didn't even see it. Carbon has the most number of bonds you can have that's shared by silicon. It has 4 bonds. The backbone of organic chemistry is carbon chemistry. You're all made of carbon. The reason for that, it is so versatile in certain bonding. It can bond up to 4 times. It can form double bonds and still have 2 bonds out either side. Everything's made of carbon. Silicon could do the same thing, but because it's a little bigger, it doesn't tend to form as long a chains. They're not quite as stable. Different world, different chemistry. There might be silicon life out there in the same way that we have carbon life. We use silicon to make computer chips, which raises interesting possibilities of maybe computer-based life forms that evolved naturally because they had a slightly different pressure and atmospheres, and they ended up with silicon chemistry instead of carbon chemistry. But that's why fundamentally this Lewis structure tells you the kind of chemistry that each one's going to have. Okay, now that we've done them on the board, you can, as an example, do it in your books. And just those 8. So you have those examples. Ha ha ha. And I will ask 8 people at random just to summarize what these are.
These aren't even the same.
I have a question. So if it's just 1, 2, 3, 4, 5, 6, 7, 8, and then like, that's how many valence electrons?
Yeah.
Okay.
And I will never ask you to draw me the Lewis dot diagram of like nickel.
Okay.
So something in the middle there, we're just not going to do in grade 10.
Okay.
But it's really useful for a lot of covalent bonding we do. So bromine and iodine, since those go away, just there's 7 valence electrons are then easy to do.
Are we doing the ones on the board?
Now they are up around you, but I'm going to just quickly ask, as we go through, just 8 random people. Matthew,
Yeah.
what would sodium look like?
Just
Yeah, I'm just checking.
dot.
I'm also checking.
Dot in the top. Oh, does it matter where that dot? So is this right and that one wrong? No.
One is more to the right.
You can put that single dot wherever you like, as long as you start somewhere. It also doesn't matter if you're adding dots if you're using clockwise or counterclockwise. So just to use this as an example, if this was like another element and I just kept going, and I was doing this, oops, there, and I just was adding dots, that's fine. And if I was doing this, and I went there, and then there, that's fine. But here's what's not fine. I add a dot, and then I decide to go backwards. That's weird. Once you pick a direction, just stick with it. I always do clockwise, but otherwise you end up with pairs when there's empty spots, and that would be very strange. Questions? Okay. Zachary,
Yes.
what would fluorine look like?
2 up top, 2 on the right, 2 on the bottom, and 1 to the left.
Excellent. Timmy, what would calcium look like?
Which one? Oh, what?
We're doing that one.
Oh,
Looking on the board here, how many valence electrons does calcium have? 2. So how would you put them on?
go on the top and to the right.
Yeah, there you go. Done. Jonathan, phosphorus. Sorry, louder. I don't think I could quite hear you. Just 2 dots? How many valence electrons does phosphorus have? Oh, let's do it right now. Looking at the board, how many look on there, sure. How many valence electrons does phosphorus have? 5? So, tell me when you're done. You're good? What does it look like then?
Two on top and then one on each side.
That's a great way to describe it. Oxygen. For me, please. Alejandra.
Two at the top, two at the right side, and then there's one.
Excellent. Zoe, iodine.
Seven.
7. So what does it look like?
So there's like two dots at the top, two dots inside, two dots in the bottom, and one dot on.
That works. Zane, selenium. Zane has left. I'm giving him negative points. Needs work. So here, selenium.
It has two dots on the top, two dots on the right, and then one.
Perfect.
I lost a point.
Yeah.
Darn. So you should do the next.
Actually, I just kept it for you.
Thank you.
So, carbon.
B?
Yep. What does it look like?
Like 4 dots. Yeah. No. Not 4. So there's one on top.
Oh dear. Now I've done that.
Okay, now I got it.
Okay. Okay. One on the top.
There's one on the top, and then there's one to the left, and one to the right, and one at the bottom.
Nice. Have you guys ever seen that? He teaches little kids how to program. They start off with how to make a peanut butter sandwich. Seen a TikTok or YouTube video of that?
Yeah, Mr. Girardo makes that.
Yeah,
do that in
yeah.
coding.
And then he actually does their instructions. So it'll say, like, the kid will say, grab a knife. So he grabs a knife by the wrong end. And the next instruction is put it in the peanut butter jar. So he throws it in the jar. And then, of course, ends up not really making a sandwich. Because very literal instructions can be interpreted very badly. Computers are very good at doing that. I don't know why I mentioned that. That's just silly. Okay. This, we're going to do this. But this is a whole thing. You know what you need now? You need a 2-minute break. Stand up, move your legs, shake your head. You can use your phones for 2 minutes. Do whatever you need to do. You need a 2-minute break.
What are you playing, Zane?
You should not be playing Fortnite. What? Who said Fortnite?
And an Apple device.
Yeah, we know. You try to ask.
You don't even know it.
What?
Oh, I'm not gonna resist this one. I like this Matthew.
Here, I don't have the video.
They're sending over.
I get so many of them.
I'm feeling loved and comforted.
Whoa, Matthew, you cannot put Karen in a headlock. No, you still can't do it in a headlock. People out there don't know. They're like, what kind of class is Mr. Neufeld run? He allows people to kill each other in class. Yeah, it's not right. It's not right, man.
Is it really killing? Like everything is killing. It's just like, am I just speeding up a process?
Also, every year, there is somebody who dies in Canada and the U.S. due to It's usually in grade like 6 or 5 because they do that sleeper hold, and then someone goes unconscious and then they don't wake up again.
But also, people on average.
And Kieran looked a little sleepy. Pardon?
Roughly 8 people a year die from slipping on carpets.
Yeah, but you didn't make them slip on carpets. If you're doing the sleeper hold, you're gonna feel a lot worse.
But what if I bought them with carpet? The school bought this carpet.
Yeah, and the school would look at that. There was an accident at a school across Canada in which their vans flipped on a ski trip. We had the same vans. We got rid of all of them. That like right away, because it turns out it was partially the fault of the van. So yeah, you do pay attention to it. The toys you buy now are different than the toys I grew up, because kids my age died with some of the toys.
Well, depending on. Speaking of some history.
The Fisher Price toys I grew up with had body sizes that were that big around that could fit in the throat and completely block the air. The new ones are about that big around. You can't get them to block the air. Pardon? Fisher Price. Yeah, it's a toy manufacturer. Yeah. Okay, that was more than 2 minutes. Back to your seats. Notes out. We're going to take these last 8 minutes and go. Did I eat Play-Doh? No, I did not eat Play-Doh.
Not eat, lick. Yeah, like put it in your mouth.
I never licked Play-Doh. No.
It has a lot of so
It actually tastes nice.
After we're done a break, I can't give breaks if we can't get back to attention. So it needs to be quick. Phones away, laptops away. I'm going to leave this here so that you can refer to it. And then I'm just going to show you how we do it. There's 2 ways to do it. This method, which is written down, is the easiest method and not the easiest. This ensures you always get the right answer for any questions you're going to get in Chemistry 10 and Chemistry 11. There is another method you were probably taught last year. It will usually give you the right answer. It's very similar to what you just did. I'm going to show you that one first. You can do both and compare them. I like the other method because it will serve you well. Is you draw the Lewis diagrams of all the individual elements. So you would go hydrogen, hydrogen, and oxygen, and just draw their Lewis dot diagrams. Yeah.
When you like get into higher level chemistry, do you use the Lewis or Bohr model more?
If I'm just doing charges in my head, I mean, they're the same model. The Lewis is just a different way of drawing a Bohr model. It just so if I'm doing anything with chemistry, I'd think of Lewis because that's the number of electrons. Bohr is just teaching you that protons are important. Yeah. So, hydrogen, might as well, has how many valence electrons, please? Let's go with Naomi. 1. So we put 1 there and 1 there.
Why, if it's 1, do you put it to the side or above?
It doesn't matter. Oxygen has how many valence electrons? Ariel. How many valence electrons does oxygen have? 1. 1? 2? Well, no. Remember? Find oxygen on the periodic table.
Oh, 8? Wait.
You're so close. So close. Start counting at the row it's in.
Oh, 6.
6. Well done. 1, 2, 3, 4, 5, 6. And then what you do is you look at all the unpaired electrons and you join them up. Now, if I join this one to that one, then oxygen doesn't get to play. So one of these atoms is the central atom. Clearly, that's oxygen, has things coming off of it. So I would just go like, oh, these must join together, and these must join together. Now, that's not how we draw it. When we draw things connected together in chemistry, like with bonding, how do we draw that? You've seen things before that are connected in chemistry, have you not? If I drew oxygen and I want to show it's a hydrogen, how would I show it's connected to hydrogen? I just draw a line. On this side, I draw another line. Yay. And then I still have electrons left over on the oxygen. I'd put them on in quadrants. Now, if you drew this like this and used the quadrants this way, that's perfectly fine. I don't care. As long as they're in quadrants, doesn't matter. You could draw them in any way you want. You could rotate it in any particular direction. They're all perfectly valid models.
Yeah, except one way it's allowed.
No, none of this. It's three-dimensional. All ways are lies. Jimmy, question? Okay. And this one goes around and around and around and around. You could draw it like that if you want to. Next up, that is how you do it if you use the skills that we just used. And it works pretty well for most things. The second method is to count how many valence electrons do we have total. We have 2 minutes left, never mind. Use the method I just showed you and try and come up with a structure for CH4. CH4. When you can show me a final drawing, you can go for lunch. Boom, baby. And I'll stop the recorder